Hello student, this is a refraction of light part 3. In this video, we will study about the sign conventions used in the spherical lenses and we will study about the formulas used in the spherical lenses. So let's start the topic. So in sign convention, first we will see the sign convention for the convex lens. So in the part 2 of the refraction of light, we completed image formation of a convex lenses, where we saw how the images are formed in the convex lens. So you can check out the video for better understanding. So in convex lens, the rule for sign convention is similar as the concave lens. So here if we draw a convex lens and concave lens, so here with respect to optical center, we divide left side and the right side. This is the right side represented as R. Here is the left side represented as L. Same way for the concave lens, with respect to optical center, right side is represented as R and the left side is represented as L. Similarly, with respect to principal axis, this is the up side and this is the down. For the concave lens, with respect to principal axis, this is up side and this is down. So right is considered as positive and left is considered as negative. Similarly, for the concave lens, right is positive and the left is negative. Up is considered as positive and down is considered as negative. So this is the sign convention rule for the spherical lenses. We can also remember this sign convention if we think about the graph. In graph, what happened? If this is our y-axis and here is the x-axis and this is the origin. So we know that x-axis is positive on the right side and the negative on the left side, and the y-axis is positive on the upside and negative on the downside. So by this method we can also remember the sign convention. So let's go to the terms used in the sign convention and their sign. So here first we will start with the convex lens. So in sign convention of convex lens, we will split the image formation into two parts. In first part, it will form the real image, and in the second part, when it forms the virtual image. When it forms the real image, that time the position of object could be at infinity, it could be beyond 2f1, it could be at 2f1, between 2f1 and f1, and the last is at f1. So these are the 5 positions of the object where the image could form the real image. Second, for the virtual, if we consider, we have only one position of the object, which is between f1 and o. So for understanding the sign convention for the real image, we can take any example based on this position of the object. So let's take beyond 2f1. So this is the image formation of the object beyond 2f1. So if we zoom it, here AB is equal to height of object, which is represented as HO. A dash B dash is equal to height of image, which is equal to HI. OF2 is the focal length, which is represented as small f. So if we mark these three values first, this is height of object, height of image, and this is the focal length. Now the distance AO is the distance between the object and optical center, and it is represented as a small u. Next is the distance of A dash O, which is the distance between the image and optical center, which is represented as small v. So here is the small v. The sign convention for a convex lens where the image is real, if we substitute the term u, v, f, height of object, height of image, and one more, linear magnification. In reflection of light, we studied about the linear magnification. I will explain it again, but first we do the sign convention. So u is present, if you see the figure, on the left side. So u will be carried as negative. V is present on the right side, so it will be positive. F is on the right side, so it is also considered as positive. Height of object is on the upside, so it is considered as positive. And the height of image is on the downward direction, so it is considered as negative. So we can substitute the value. U is negative, V is positive, F is again positive, height of object is positive, height of image is negative, and M, which is the linear magnification, is considered as negative. So linear magnification is negative because it is a real image. Similarly, if we go for the virtual image of a convex lens, so here the image should be virtual. So virtual image is always formed between f1 and O. So let's draw the image formation of convex lens when the object is between f1 and O. So A dash B dash is the height of image, which is positive. AB is the height of object, which is also considered as positive. Focal length is also considered as positive. U is negative and V is negative. So there is a sign convention change between the real image and virtual image of a convex lens. So if we write on the table, U will be considered as negative, V will be considered as negative, F is positive, height of object is positive, height of image is positive, and M will be positive because it forms a virtual image. So this is a sign convention for convex lens. Let's move to the sign convention for the concave lens. So here in concave lens, we always forms the virtual image. So if we take the image formation for a concave lens, here AB is the height of object. A dash B dash is considered as height of image. OF1 is the focal length and the length of O to A is considered as U and the length of O to A1 is considered as V. So you see U is present on the left side, so it will be considered as negative. Height of object is considered as positive. Height of image is considered as positive. Focal length is considered as negative and V is considered as negative. If we draw this on the table, so here U will be negative, V will be negative, F is negative, height of object is positive, height of image is positive, and M is positive because it is a virtual image. So I hope you understood the sign convention of the spherical lenses properly. Now we will study about the linear magnification formula and the lens formula. Now we will study about the linear magnification. Linear magnification is defined as the ratio of the height of image to the height of object. Height of image is represented as hi. Height of object is represented as ho. So linear magnification is, which is represented as small m, is equal to height of image to the height of object. M is equal to hi by ho. This is equal to v by u. V is the distance between image and the optical center and u is the distance between object and optical center. So this formula we will use for solving the numericals. M is equal to positive, it forms a virtual image, and when M is equal to negative, it forms real image. If M is positive and magnified image, so it will be a convex lens. Similarly, When m is positive and diminished, so it will become a concave lens. And when m is negative, so it will always a convex lens. We can remember these points. Now we can move to the lens formula. When we are using a spherical lens, then the relation between u, v and f forms the lens formula. In the spherical lenses, the relation between principal focus, focal length, distance between the object and optical center, and distance between the image and optical center. So the lens formula is 1 by f is equal to 1 by v minus 1 by u. Here we can use sign convention. It means that the sign of u, v and f will depend upon the lens. If it is a concave lens, we will use the sign convention of a concave lens. If it is a convex lens, we use the sign convention of the convex lens. We will solve few questions based on this topic. This is the first question. It is mentioned that there is a concave lens of focal length 15 centimeter. So if it is a concave lens, then we use the sign convention of a concave lens. Focal length is 15 centimeter. At what distance should the object from the lens be placed so that it turns an image at 10 centimeter from the lens? So image at 10 centimeter from the lens. It means that V is given. And what we have to find? U. After that, we have to also find the magnification produced by the lens. So first we write the given focal length. For concave lens, focal length is negative. V is given as 10 centimeter. So for concave lens, V is always negative. So it is minus 10 centimeter. And what we have to find? Magnification and the value of U. So we can use the lens formula, which is 1 by f is equal to 1 by v minus 1 by u. And substitute the value. F is minus 15, 1 by minus 15. V is minus 10. So we can write 1 by u is equal to 1 by minus 10 plus 1 by 15. By taking LCM, we will get it as minus 1 by 30. So U is minus 30 centimeter. Now we have to find the magnification. So we will use the magnification formula, which is M is equal to HI by HO, which is equal to V by U. So in this question, we have U and V value known. So by substituting these values, M is equal to minus 10 divided by minus 30. So it will become 1 by 3, which is equal to 0.33 plus. So we can say that it is virtual and erect, and it is diminished. Why it is diminished? Because M value is less than. So when M value is less than 1, it means it is diminished. Image is here diminished. Let's move to the next question. In this question, a 2 centimeter tall object is placed perpendicular to the principal axis of a convex lens. So first we need to see which lens is present here. So it's a convex lens. And then after that, we will use the values to solve the problem. So here height of object is 2 centimeter and the focal length is 10 centimeter. The distance of the object from the lens is 15 centimeter. So this is our U. So in this question, height of object, focal length and the distance of the object is given. What we have to find? We have to find the nature, position and size of the image. Means you have to find the V value and height of image, and also we have to find the magnification. So first we note down the given values. Height of object is given as 2 centimeter and it is considered as positive. Focal length for a convex lens is positive, so it is plus 10 centimeter. And the distance of the object, which is U, is minus 15 centimeter. What we have to find? V, height of image and magnification. First we will find the value of V by using the lens formula. 1 by F is equal to 1 by V minus 1 by U. And F is plus 10 centimeter. V we have to find, and U is minus 15 centimeter. 1 by V will be 1 by 10 minus 1 by 15, because this minus and minus becomes plus, and when we transpose to other side it will again becomes minus. By taking the LCM, 1 by 30, so V is equal to plus 30 centimeter. Now we can find the height of image by using linear magnification formula. M is equal to HI by HO, which is equal to V by U. Now we substitute the value of V and U. So M is equal to V by U. U is minus 15 and V is 30. So it will become minus 2. So M is equal to minus 2. M is a unitless quantity. Next we have to find the height of image. So M is equal to height of image by height of object. M is minus 2, Height of image we have to find. Height of object is 2. So height of image will be minus 4 centimeter. When m is negative and magnified, so the image is real and inverted and magnified. So this is the nature of image. If you practice more questions based on refraction of light, it will give you more confidence. Now we will move to the next topic, which is power of the lens. Suppose we take a convex lens. This is the optical center, focus. If we take an incident ray, which is parallel to the principal axis, so what will happen? It will converge. Suppose now, if this f2 will move more towards the optical center, like suppose here, this is our new f2. And if we take the same incident ray, then what will happen? It will pass through the f2 dash, means new focus. So what you would noticed, if there is no lens, then this ray, then this incident ray would have to go this way. Okay, fine. So if I consider this angle as degree of convergence, suppose this is theta, and similarly for the new focus, this is the new degree of, this is the new degree of convergence. So here theta dash is greater than theta. It means that when you are taking focus as f2, and when you are taking the focus as f2 dash, so f2 dash will converge more than f2. Why? Because focus is moving towards the optical center. If it goes more towards the optical center, more it will converge. Fine. Similarly, if we take a concave lens, then what happened? This is a concave lens. Here is the optical center, f2, 2f2, f1, 2f1. Let's take the incident ray parallel to the principal axis. So it will diverge and it will pass through the f1. Now this f1 moves towards the optical center. Suppose this is a new f1, new focus. So let's check the incident ray, which is parallel to the principal axis. So what will happen? It will diverge and it will pass through the f2. So if there is no concave lens, then what could happen? This incident ray has to follow this path. This incident ray has to follow this path. You can name it as this incident ray as 1. And this is the second. And with respect to second, it could follow this way. So here, this is our theta and this is our theta dash. So theta dash is greater than theta. And what is here theta and theta dash? These are degree of divergence. So how much the incident ray getting diverged, or you can say how much incident ray getting conversed, this is decided by the degree of convergence and the degree of divergence. This degree of divergence and convergence is called as the power of the lens. So we can define the power of lens as the degree of convergence or divergence of the spherical lens is called as the power of the lens. It is reciprocal to the focal length. The formula for the power of lens is equal to 1 by f, and f is here the focal length. And one thing always remember, f must be in meters. Means f we are using it as a meter. The SI unit of power is diopter. It is represented as capital D. So 1D, which is 1 diopter, is equal to 1 by meter, which is equal to 1 meter inverse. So one thing we can note it down, when power of the lens is equal to positive, it means that it's a convex lens. Means if I say P is equal to plus to D, so what will happen? If it is plus, it means it's a convex lens. And why it is a convex lens? Because if P is plus, it means that focal length is positive. Why focal length is positive? Power is equal to 1 by f. So when f is positive, then P is positive. So it means that focal length is positive. And with the help of sign convention, if focus is positive, it means it's a convex lens. Similarly, if our power of the lens is negative, it means it's a concave lens. Same method is applied here. If our power is minus 2D, so here minus represents concave lens. Why it is a concave? Because power is negative when focus is negative. It means that focal length is negative in concave lens. I hope you understood this part properly. Practice more questions so it will be easier for you to clear your concept based on this chapter. Thank you.